We go. You're welcome, everybody. Sorry, we're a couple of minutes late starting today. You're very welcome to the Women in Geospatial webinar today. And this week or this month, we have two academics. We have Daly from University of Galway, who's beside me here. And we have Gemma Casal, who's at Maynooth University. And they are going to introduce themselves. So I'll let Eve go ahead first, and she's going to give us a presentation on herself and her work.
Hi guys, nice to meet you all, and thank you, Jenny, for inviting me. I'm just going to share my slide, and then I'll tell you a little bit about me and all that. So, okay, can you see my slide? So that is me, basically, out doing field work. So I am a geophysicist, a physicist by training, actually, but I'm a farmer at heart and a scientist of the mind. And I think over the last few years, I finally started to bring those bits of my life together. This is a picture of me doing remote sensing. I basically have a device that generates an electromagnetic wave, sends it into the subsurface. It interacts with the subsurface, and if the subsurface is conductive, either in terms of what it's made or water content, I can map spatial differences. So I suppose I'm mostly interested in processes, and I'm mostly interested in what's happening beneath the surface. But I am not averse to using variation. Say if you're using satellite imagery, you can see spatial variations in land cover. They're often driven by what's happened in the subsurface. So why isn't that moving forward? Yeah. So facts about me before we kind of get into exactly what I do and why I do it. I'm a woodworker, a triathlete. I spend a lot of time in nature, adventuring, working on a farm. And I'm also a member of the Civil Defence in Ireland, which is a volunteering organisation. And actually, in my latest research project, I finally will get to bring that civil defence into it. And I think by the end of this presentation, you'll kind of see that all of these facets of my personality are well used. So basically, my focus is on a region in the Earth that we call, Earth scientists increasingly call the critical zone. And the critical zone is simply defined as the region from the top of the canopy, so tree cover, to where we get water in the ground. So it's quite a large vertical area. We call it the critical zone because it's critical to where we get to us. It's where we get our oxygen, it's where we get our food, it's where we get our resources. And within that also, it's also increasingly where we dump crap and where we're actively not managing, for example. So to study the critical zone, it's a really complicated area. It's made up of the solid matrix of the subsurface, also the biosphere on top, so plants, microbes, soil, fluids. And very much within the critical zone, you have the structure of it, what it actually could be used for, and increasingly we've now starting to get the tools where we can actually start to look at various biogeochemical processes across this critical zone. And the fun thing of it from a geophysicist perspective is you get to use lots of interesting technology, both to map its various layers. And just to say where I come from, my original PhD came from, I was funded by the oil and gas industry. And basically I was looking for oil and gas offshore Western Ireland. So back then, 30 kilometres below the surface was where I was working. Now I'm working within 1 to 2 metres of the surface. So effectively I'm getting shallower with age, hopefully only in my research and not in my character. And I suppose if I had to come up with a catchphrase for what I do and what I explained to my mum is how we see beneath the earth without digging, because we don't want to dig holes if we don't have to, and digging holes is expensive. And in somewhere like Ireland, you could walk 10 metres and find that the hole you dug is completely different than the one 10 metres away. So, sorry, now I'm having trouble with my PowerPoint. It's just not, yeah. So basically, critical zone. So what is geophysics? So I've sort of described the critical zone, and geophysics is basically a way of sending electrical signals or any signal into the ground and measuring the Earth's response, or observing the Earth's response to a natural signal. The powers of geophysics is we can opt at a variety of spatial scales. So we can look at very small scale to very large geographical spatial scales. Fundamentally, generally, the physics is kind of the same. It's just the volume of data changes. We're increasingly also, with the sort of miniaturization of technology, tools that we used to be able to use for very deep crustal work, we can now apply, for example, put something, advent of drones would be the classic example, and we can also make sensors that are now small enough to sit on a drone and low cost enough that we can actually use them at field scale, where historically we wouldn't have been able to. So we're increasingly able to use geophysics across a variety of spatial scales. And you might say, why does this matter? Well, even if we take something like soil moisture or how wet the soil can be, that can be wet at a point. Wetness can be over a field. It can be over a catchment. And actually how soil moisture changes and some of the drivers is going to be different depending on what scale you're working at. So you need a tool that can monitor soil moisture at a variety of those spatial scales in order to tease that out. Geophysics is traditionally moving away from just doing one survey. So if you're looking for oil and gas, you can go out and do one deep survey, seismic line, and you can find that that's where your reservoir is, or that's where your mineral deposit is. If you come back next week and do that survey again, nothing will have changed. It's 30 kilometers down. There's been no change in the Earth's structure. Once you start looking at the soil layer, you know, you could have a farmer, they could have been ploughing, they could be growing different crops. Over time, it could be different, which can cause ultimately changes in compaction. Also, it's much more heterogeneous. So actually starting to do repeat surveys, because some properties change rapidly in time. Some properties don't really change in time at all. So like what a soil is made up of over a 50-year period may not change, but the water content in that soil can change depending on other processes. So we can, moving away, so we're sort of borrowing from geology and starting to or borrowing from biology and doing repeat experiments and replicates. And this would be something that a biologist would be very familiar with. We're also gathering huge amounts of data, as probably lots of you are aware of, because we're all into sort of geospatial data sets. So actually integrating different layers and using advanced data analytic tools, machine learning, for example, are increasingly coming into geophysics. So geophysical methods can broadly be divided into two categories. One is active, so we create a signal, subject that signal to the Earth's surface or subsurface and measure the response. Or we can have passive, so we merely observe the Earth's response. An example of this is here, two techniques that one, ERT, injects an electrical current into the ground, and the image on the left is basically a profile across the field where you've got distance on the x-axis, depth on the y-axis, and each color represents areas in the ground where the electrical current is flowing differently. Main driver either been water content or the physical properties. The other instrument, which I'll show you an example of a few minutes ago, is we're generating an electromagnetic wave, like the very similar to how your mobile phone works. That signal is sent into the subsurface, and as it's moving, so the benefit of this technique is as you're walking or pulling it behind a bike or some sort of towing device, you can map how, again, how electrically conductive the subsurface is, because the more conductive the subsurface is, the more the subsurface is going to interact with that electromagnetic signal. And I use both of these very much to look at sort of identifying soil type, for example, peat soils, and soil moisture. An example of a passive geophysical technique would be an example of just looking at the Earth's response to its gravity field. Most of you have probably done some bit of physics somewhere along, and you've all heard that gravity is 9.81 meters per second squared. Well, if I told you you had an instrument that would have a sensitivity on the order of 10 to the 6 and 10 to the 9, it turns out gravity is not constant over the Earth. And the reason being that is the subsurface density changes spatially. So therefore, that if you have an instrument that's sensitive enough, you can detect those changes in gravity. So we're not creating any gravity signal, we're basically measuring the Earth's response and the Earth's materials response to gravity. So just to show an example of the previous technique, so using the electromagnetic technique, I was approached by some colleagues from Romstad Research Institute in the UK, who are very interested in monitoring how much cows dairy cows, how much they compact the soil as they wander around a field. So they came and showed me this video. They basically had a GPS device, recording device, put onto the various cows. Each cow is a different colour. So as I'm talking, really, I should hit play. And it turns out we can model how cows move around a field. And I did say I am a farmer, and this does ring true to me, that generally you'll find that cows, they will be grazing in a small area in the field, and then at some point they're going to move somewhere else. So we can kind of model this. So the question is, what compaction do they cause? I mean, a cow is weight, going to be a ton, or depending on how big they are, there's going to be a spare weight in a cow, and as that cow moves around, it's going to compact the soil. Why do we care about this? It turns out if you compact the soil, you change the electrical signal response to the ground, and this has an impact on CO2 emissions. So by measuring in a field where you've got compaction due to cows wandering around the place, we can kind of more accurately work out what are the greenhouse gas emissions from farming in that field. So that's kind of ultimately what we were doing the project for. And this is you can.
Yeah. Do you know what was growing in this field? Is it the regular ryegrass or is it
regular ryegrass? Yeah.
And the second one, are they using like these envelopes for cows feeding, that it will be separated, let's say horizontal, vertical, or like whatever, or they just provided the field over the
They've got 24 paddocks across this field, so there's a grazing pattern.
So
they have a grazing pattern. So you know, like we have data on kind of how long they spend in each field, and they use patent chocolates as pasture base. So we have some idea of like amount of grass growth, and that's all fed in. So just to show you this instrument in action, and I kind of did mention I like woodwork and a farmer at heart. So I'd actually spend quite a bit of my time when I'm out doing geophysical surveying. The farmer has to come on. So I've often had to like herd cattle because, they will tell you, the farmer, there is no stock in the field, and then you rock up and suddenly there is. But here is one student where we were actually taking a field. This is the electromagnetic instrument. You might recognize the GPS antenna. We built this wooden frame to carry our instrument on board. No metal. Obviously, any metal will interfere. Remember, I'm sending electrical currents into the ground. So basically, it's sort of a wood frame. And this, fair play to this fourth-year student. She spent 2 weeks one summer driving up and down the field at a 1 meter line spacing at very slow speed. But ultimately, with some modelling, and this is a paper that we've currently in review, and these were the paddocks on the right-hand side that you can see here. These paddocks are on the right-hand side where they've colour-coded to where we've regions of compaction and where there's regions of less compaction. And of course, you could then work out the overall area and kind of then figure out how much compaction it is and relate it to greenhouse gas emissions. So that's an in-field example of one of my projects. Going to a passive geophysical technique, so this is one where we measure the Earth's response. It turns out that most rocks are naturally radioactive to some degree, some more so than others. So there is a plane, if you have basically the TELUS plane run by the GSI, has a geochemical soil survey, but it also is flying basically a fancy Geiger counter on board that can measure the amount of uranium, thorium, potassium, which are gamma ray spectrometer data, radioactive elements. So you've all heard of radon. So these are just similar type elements, and a total count. And as this plane is moving over the landscape, it is basically, if you think of it as like a flashlight emulating the Earth's surface, and it's measuring those 4 elements, how they are coming off the Earth and been recorded on the plane. And over the last 10 years, the Geological Survey of Ireland has been flowing this data set at a line spacing of 200 metres, and they can create a grid with a 50 metre pixel resolution. And on the right is the map so far, and I believe they're going to have it finished off in Kerry this summer. So a few years ago, if you actually look at maps of the uranium, thorium and potassium, different soils, you can actually see different soil types. For example, peat versus, say, more sandy, gravelly soil. You could actually see, if you looked at national soil maps and the TELUS map, there were similarities. And I was wondering, could we use this for soil mapping? And to start off with, we decided to look at peat soils. So it's sort of one of the main groups. About 25% of Ireland is covered by peat soils. And often some of that peat is hidden, as in if you look at a satellite image, it just seems like a grass field. It's only if you dig a hole do you realise it's peat underneath. So it turns out that peat has a very special radiometric signature, i.e. peat is not radioactive. And peat, when it's wet, the wetter the peat is, it absorbs the radiometric signal, the gamma radiation that's coming from the rock underneath. So we're all hearing about looking for hot spots. I'm looking for low spots. So regions where there is no radiometric signal, very little uranium, thorium, potassium, and talked about, is potentially an indication of peat. Where if you've got a mineral soil, so a soil that's made up of more, your traditional clay, sand, silt, that is going to have a radioactive element as well as the bedrock. So you kind of get areas of increased radiometric response. And actually, we're increasingly interested in mapping the transition from one to the other. And that has implications, will have implications for rewetting. So the first question was, could radiometric, this is an all work-based PhD student of mine has just completed. Can radiometric data discriminate between peat and non-peat soils? And can we map inter-peatland variation? So even if you take one large peat bog, might be 20 kilometres by 20 kilometres in the Irish Midlands, it turns out the radiometric signal is different from different areas of that bog. So the question is why? What is going on there? And could we use machine learning to create a framework for monitoring peatland restoration? So the idea we had was, could we integrate the 4-band, so that's the TELUS plane there on the right hand side with 4 bands, and if we took some Sentinel-2 imagery, could we combine these into kind of a more useful land cover classification of what's actually happening within peat bogs in Ireland? So first off, could we identify peat or non-peat? There are several national databases and maps that show peat extent in Ireland, but most of them are based on either very poor spatial resolution or from optical satellite imagery. So if you can see it's peat, it's peat. But what about this peat that's covered by grass? And we basically used machine learning. We used neural networks, a neural network solution. So I'm just comparing. And the main GIF that's flicking over and back, it's sort of the QGM is the Geological Survey Quaternary Geology Map, and our neural network map is the ANN. But if we move to the orange box on the main image, you can see that's blown up, and it actually, within the 2 smaller boxes on the right, you could see that there is a Bordnamona bog. The yellow boundary of which is the actual land boundary, owned boundary of Bordnamona. And you can see on the Quaternary Geology map, of course, the subsurface doesn't, a lot of maps as well into national maps, say ISIS, for example, a lot of where you've got a peat at non-peat, when you zoom in, the boundaries are dictated by the actual owner, the land boundary, as opposed to the actual soil type itself. But the really interesting thing we found out using the artificial neural network map was we were able to identify, remember the TELUS data has a pixel resolution of 50 meters. So 1, we could actually identify peat where there was grassland or under forestry, and 2, we could identify much smaller pockets of it. And in the on the lower image on the ANN, you can see the small box there that has 2 peat pockets that have been identified that were not visible really on any other national map. And 1 was underneath grassland and 1 was underneath forestry when we went out and ground truth it. So it was a good first pass. As part of Dave's postdoc, he then stepped up. We basically applied this to all existing data for all of Ireland, and now basically have created a map of Ireland of where there's peat at non-peat, and it's working really well in the Irish Midlands. Hands up, no technique is perfect and no solution to everything. There is a challenge using this in rugged regions and in regions where the geology changes rapidly over an area. So, we'll never say that this is the TELUS map is the peat map of Ireland. It needs to be integrated with some of the other results, but definitely in the Irish Midlands and beneath grassland sites, it's working really well. Coming back to the inter-peat variability, I think most of this group would be familiar with satellite Earth observation data sets. So you're used to seeing spectral signatures, for example, of different land cover types. So I thought this was quite clever what Dave did. He decided to add the radiometric data and regard them as a band, as a satellite band, essentially. So in this graph, effectively what we've done is, again, he used a neural network, unsupervised SOMS network, to actually classify all those. I previously mentioned all the bands that in this image, the 13 bands of satellite of S2 data and 4 bands from the TELUS radiometric dataset. He fed all of those bands, or 17 bands, into a SOM system and classified them. And here is color code. So ended up over this bog, peat bog in the Midlands. It turned out to be kind of 3 clusters. Interestingly enough, there seemed to be a cluster very much in the middle and then a cluster around the edges. So come back to what I mentioned about transition zones. It's kind of hinting at something there. And if you look at the graph, we've color coded each plot, or each line in the graph has been color coded to the same cluster polygon in the map on the right. So say, for example, the green cluster, the brown one, is the brown line on the brown graph. And what we really noticed, which was quite exciting, was effectively you're looking at land cover if you're looking at the satellite bands, but you're looking at subsurface variations when you were looking at the radiometric data. And you can see where I've highlighted a circle called Optram. But on one side of that red dashed line, you can see that there is higher reflectance in the short wavelength infrared band in cluster 3, where it has the lowest radiometric response. So what you're seeing is effectively here that we're seeing that peat surface is dry at the surface, but it's actually wetter beneath. So you're actually kind of creating an integrated, so that cluster information is giving you an integrated interpretation of what's happening both on the land surface and underneath. So that is something that we're also still developing. And now we really want to zoom in to looking at that transition zone where we go from peat to kind of where we go to mineral soil outside of the bog. And but remember, 50 meter pixel resolution might seem fantastic for a national scale data set. It's not very good for on-farm planning, or if we're planning to actually go re-wetting some. There's lots of talk in the Midlands about re-wetting some of these soils. So if you've got a farmer who's going to re-wet a mineral soil or an organic soil in the Midlands, but the farmer next door doesn't want that re-wetting, you kind of need to know what impact. And whatever you do in your farm isn't going to stop at your fence or your ditch. It's going to have an effect. So the next part of this project is put it on drones. I've also started using, again, and I won't go into any detail here, this was just published, but there is a model that allows us to extract soil moisture from Sentinel-2 data. And we all know the problem in Ireland of Sentinel-2 data. We can't get a huge time series, but we kind of asked the question, if we know about in-farm management, so we know what's happening in a farm, can we use sort of like, can we get a series of images, even if they're over 4 or 5 years, do certain parts of the farm considerably be wetter or drier consistently? You know, we mightn't be able to quantify exactly how wet or how dry, but is relatively one area wetter than the other. So we've started doing, the part of a Walsh Fellowship, we were using some of this Sentinel data to work on that. I'm not going to spend any time on that because it's a slight aside. But coming back to the radiometric signal, we have this national data set of airborne radiometric. It was only flown at one timestamp. But what if we could fly repeat measurements over the same farm, and over like a year, the subsurface soil isn't going to change physically, but wetness might. So can we actually do temporal surveys of radiometrics to actually monitor soil moisture? So I have recently, thanks to iCrag, I have bought a drone-based system and now we can put a radiometric sensor on board, and we're going to be doing repeat surveys. And this is part of some ongoing projects I have. So one is a project Re-Wet, funded by DAFAM, working with Teagasc. So we're basically trying to integrate water table measurements, ground geophysics and radiometrics, and using several farms in the Midlands where we're actually blocking drains, monitoring re-wetting and trying to assess technologies of how, where and the impact of it. Another project scaling up on the kind of re-wet will be to deploy this nationally over the whole country, and that project is Detect. And I suppose finally I did say, how does the civil defence come in? Well, radiometric sensor not just gives you the amount of uranium, thorium and potassium, but also can give you a dose rate. So how much natural gamma radiation are you exposed to. And one of the Civil Defence's remit is to monitor soil samples, take soil samples and monitor, calculate dose rates for the human population. So as an EPA project that is just, I've been asked to kind of come on board with my TELUS experience, can we actually create updated outdoor gamma radiation dose map for Ireland? And I would like to really sort of put my civil defence hat on and work with civil defence, bring the EPA, the GSI, all of us together to inform a national mapping, actually go out and gathering samples, but remember, leverage the TELUS data set that's been flown over the whole country. And one of the main interesting things from a rewetting perspective, the wetter the soil, the lower the dose rate. And I'd like to assess that using drones at various other technologies on key sites around the country. And that's going to keep me busy for the next couple of years. And we're looking for any PhD students. So if you know anybody who wants to come and do a PhD, come and have a chat. So finally, just to say, most of the time when you're dealing with the critical zone, it's very complex, very complicated, and I look confused a lot of the time when I'm out in the field. Thank you.
Thank you very much, Eve. That was great. We have time for one or two short questions. If there's anyone out there that has a short question.
You stop sharing, yeah.
Stop. Do we have, if you can raise your hand or put questions in the chat. Gamma mapping, how long are they valid for? A few years or a decade?
Well, in terms of the radiometric, it literally is a time when it was flown. And that map of Ireland would have been flown in different blocks over a 10-year period. So for the most part, it should be, unless there's any changes, you know, in a particular region. So it will probably in the Midlands where there's a lot of change in water, that'll be a change. But there won't really be a huge change in the actual dose rate from the soils. We're talking such short periods of time. If you think of half-lives as some of, remember you go back to your radius, yeah. So like it is valid. I'm kind of looking at, can very small variations temporarily be used for soil moisture, which is slightly different. But the gamma mapping, the map itself is valid for the bedrock. That's not going to change with time.
Thank you very much. And I have a question about the EMI. So we're also looking at rewetting and monitoring some of the rewetting that Bord na Móna is doing in the Midlands in another project. And can you tell anything about the water table from your EMI measurements?
You can. It's trickier. Do this again. You do temporal surveys. You know, you'd kind of do it in the middle of summer where it's pretty dry, and then do it again. It'd be a lot of effort, you know. You'd almost a few wells might be easier. But there are researchers doing it in Germany. There's quite a lot of active work, and there are people trying to put EMI systems on drones. But we're probably 5-10 years away from getting good data out on that one.
Okay.
But yeah, I can.
That's not going to work for our project then. Thank you so much. If anyone else has questions, you can put them in the chat there, and maybe we'll cover them at the end.